Okay, good morning. Welcome to the class. Today, let's have a look at the seventh lesson in chapter 5. We're going to have a look at the cross product of vectors. Okay, first of all, let's have a look at the learning goals. After this lesson, you are expected to be able to understand the concept of the cross product of the two geometric or Cartesian vectors in three-dimensional settings. Then find the cross product of two geometric or Cartesian vectors in 3D. Understand the main properties of the cross product of two vectors in 3D and use them to solve related problems. Then understand the concept of triple scalar product and use it to solve related problems. Last, solve application problems related to cross product. Okay, first let's have a look at an introductory example. So consider using a wrench to tighten a typical bolt that is holding two pieces of wood together. Suppose the force vector F on the wrench turns it clockwise, as shown here in this diagram. The length of the handle of the wrench is represented by the vector R. The effect of turning the wrench is called the moment, M, of the force about the center of the bolt. The magnitude of M of the moment depends on the distance, the magnitude of R, between the bolt and the point at which the force is applied, and on the magnitude of the force perpendicular to the wrench. From the diagram, we know the magnitude of force is the magnitude of F times sine theta. Therefore, the magnitude of M equals the magnitude of R times the magnitude of F times sine theta. In this case, the direction of the moment is into the bolt, so the bolt is tightened. If the force was applied in the opposite direction, the direction of the moment would be out of the wood and the bolt would be loosened. So in order to describe a scenario like this, we introduce the concept of cross product. Okay, so next let's have a look at the concept of cross product of two geometric vectors in 3D. So in general, the cross product of two vectors, u and v, is defined as the cross product of u and v is the magnitude of v times the magnitude of v, the magnitude of u times the magnitude of v times sine theta, then times the vector n. This is a geometrical form of the cross product, where theta is the angle between u and v, where theta is between 0 degrees and 180 degrees. And vector n is a unit vector perpendicular to both u and v, such that u, v, and n form a right-handed system, as shown here on the right. As the fingers on your right hand curl from u and v, your thumb points in the direction of the cross product between u and v. This means that the order of the vectors u and v is important in determining which way the cross product vector points. Note that the cross product u and v is read as vector u cross vector v, not vector u times vector v. Okay, do you have any questions? Do you need more time for this? Okay, so next, to determine the magnitude of U cross product with V, consider the parallelogram formed by vector U and V. The area of the parallelogram is given by this formula area. Area equals base times height, right? So sine theta equals h over the magnitude of V. Therefore, h equals the magnitude of V times sine theta. Then we have the area of the parallelogram equals base times height, which is given by the magnitude of U times the magnitude of V times sine theta. Thus, the area of the parallelogram formed by vector V and vector U, or back vector U and V, is equal to the magnitude of the cross product of U and V. You understand? Okay, if you don't have any questions, let's consider an example to get you familiar with the concept here. If the magnitude of the first vector u equals 30, the magnitude of the second vector v equals 20. The angle between u and v is 40 degrees. And vector u and v are in the plane of the page, as shown here in the figure on the right. Can you find vector u cross product vector v, and then vector v cross product vector u? Okay, I'll give you 4 minutes to have a look at this question, okay? Okay, have you finished? Okay, let's have a look at the solution together. Okay, question A. Using the right-hand rule, the direction of u cross v is outward from the page, right? So we can let n hat be the unit vector perpendicular to both u and v, with direction outward from this page. Then we have the following relationship: u cross v, by definition, equals the magnitude of u times the magnitude of v times sine theta, then times the vector n hat. Okay, then let's put all the values in. That's approximately 38.6 n hat. Well, n hat is the unit vector perpendicular to both u and v with direction outward from this page. You should specify the magnitude of direction of n hat. Remember this, okay? In question B, using the right-hand rule, the direction of v cross u is into the page, right? Always use the right-hand rule to find direction of the cross product. Thus, we know v cross u equals the magnitude of v times the magnitude of u times sine theta, then times negative n hat, right? Because this time the direction is into the page. So that's negative n hat. Again, put all the values in. That gives us negative 38. Oh, sorry, negative 38.6 n hat. So from this example, we can see that u cross v and v cross u are not equal vectors, but they are opposite vectors. The cross product is not commutative, which means u cross v is not necessarily equal to v cross u, but u cross v equals negative v cross u. Okay, any questions? Okay, so that's the definition of cross product of two vectors in the geometrical form. Next, let's have a look at the definition of cross product in Cartesian form. So we want to develop a formula for A cross B involving components. We can let vector A be A1, A2, A3. Three components are A1, A2, A3. And let vector B is B1, B2, B3. Then first of all, we find the magnitude of the cross product. The magnitude of A cross B, by definition, is given by the magnitude of A times the magnitude of B times sine theta, right? Then we can square both sides. Squared magnitude of the cross product on the left equals magnitude of A squared times magnitude of B squared times sine theta squared. And the right side can be rewritten as magnitude of A squared, magnitude B squared times 1 minus cosine theta squared, right? And expand that to be magnitude of A squared times magnitude B squared minus. Also note that the second term in the expansion, magnitude of A squared times magnitude of B squared cosine theta, is actually the dot product between A and B then squared, right? You follow me? Okay, so now we can find the magnitude of A squared, which is actually A1 squared plus A2 squared plus A3 squared, right? And the magnitude of B squared is actually B1 squared plus B2 squared plus B3 squared. Then the dot product of A and B squared is actually A1 B1 plus A2 B2 plus A3 B3 then squared, right? Then we can expand everything. And then rewrite setting up perfect squares. Then that gives us the result here. You can try to work on this after this class, okay? Try to do it yourself. Then we have arrived here, which is written as the squared magnitude of A2, B3 minus A3, B2. A3, B1 minus A1, B3. A1, B2 minus A2, B1. Thus, we know the magnitude of A cross B is actually the magnitude of this vector, whose components are A2, B3 minus A3, B2, A3, B1 minus A1, B3, A1, B2 minus A2, B1, right? Can you follow me? Okay, then let vector C represent the vector on the right side of the last equation. The three components of C is A2, B3 minus A3, B2, A3, B1 minus A1, B3, A1, B2 minus A2, B1, okay? And then we want to check if C is orthogonal to A and B, right? So note that we already know that the magnitude of C is the magnitude of A cross B, right? So next, let's check if the direction of C is orthogonal to B and A, right? So vector C is orthogonal to A if the dot product between C and A is 0. So let's check that. So if you find the dot product between C and A by putting all the coordinates in, then actually you find the dot product between C and A is 0, right? Thus we know vector C is orthogonal to vector A. Also use the same method to check if B is orthogonal to C as well. Of course, by putting all the numbers, all the coordinates in and collect like terms, then you can also find the dot product between vector C and B is also 0. Therefore, we also know that C is orthogonal to vector B. Since vector C is orthogonal to both A and B, and the magnitude of C equals the magnitude of A cross B, we know that C is either A cross B or negative A cross B, right? According to the definition of cross product. Can you follow me? Then we need to check which one is correct. Is C equals positive A cross B or negative A cross B? So we can do it like this. According to the previous analysis, there is one and only one correct option between the two expressions, right? Which means A cross B is either A2 B3 minus A3 to B2, A3 B1 minus A1 B3, A1 B2 minus A2 B1, or the negative of that vector, right? So next we need to check which option is correct. Okay, we can check that by considering a special case. When A1 is 1, A2 is 2, A3 is when A1 is 1, A2 is 0, and A3 is 0. And B1 is 0, B2 is 1, B3 is 0. That means we consider two unit vectors along the x and y direction, right? In this case, according to the geometric definition of cross product, we know that A cross B must equal I cross J, which gives us actually K, right? In the special case, which is 0, 0, 1. Then we check A2 B3 minus A3 B2. By putting all the numbers in, this gives us 0, right? And A3 B1 minus A1 B3, this also gives us 0. And A1 B2 minus A2 B1, this gives us 1, right? Therefore, we know the correct option must be the first one, right? Which means A cross B is given by the following vector, which is A2 B3, A3 B2. That's the x component. The y component is a3b1 minus a1b3. The z component is a1b2 minus a2b1. That's the Cartesian form of A cross B. Can you follow me? Of course, there is a visual way to remember how to perform these operations, like shown here in the figure in the bottom. Okay, so in the first row, just list I, J, K, I, J, K. These are the unit vectors along the three directions. In the second row, list the three components of the first vector A, A1, A2, A3, A1, A2, A3. And in the third row, list the three components of the second vector, B1, B2, B3, B1, B2, B3, right? And the resultant cross product can be found like this. So first of all, the coefficient for I is given by the product of the two numbers in the diagonal here, A2, B3, right? And minus the product of the two numbers along the reverse diagonal, as shown here in the line highlighted in blue, minus A3B2, right? You can do the same thing for the component J and K as well, right? Okay, I'll give you some time to have a look at this. Okay, so here we know the Cartesian form of the cross product between two vectors, right? So let's have a look at an example. Consider the vectors A is 7, 1, -2. Vector B is 4, 3, 6. So basically, we know the three components for vector A and B, right? Can you find A cross B? According to what we have learned so far, can you find A cross B? Okay, I'll give you 3 minutes to have a look at this example. All right, let's have a look at the solution together. So as we said, it's better to draw a diagram to help you to find the cross product like this, right? So A cross B is given by 1 times 6 minus 3 times negative 2i. That's coefficient of I. Then coefficient of J is negative 2 times 4 minus 6 times 7. Then coefficient of K is 7 by 3 minus 4 by 1. Then 3 components of A cross B is 12, negative 50, 17. Okay, any questions? Okay, so we have talked about the definition of cross product geometrically and in Cartesian form. Then let's have a look at the properties of the cross product. So for any vectors u, v, and w, and any scalar k belongs to the real number set, we have the following properties. First, u cross v equals negative v cross u. We have already seen this in previous examples, right? Next, u cross the sum of v and w equals v cross u cross v plus u cross w. Next, the sum of u and v cross w equals u cross w plus v cross w. Next, if u and v are non-zero, u cross v equals 0 vector if and only if there is a scalar m belongs to the real number set such that u equals m times v, which means u and v are collinear, right? Okay, last, the scalar k times the cross product of u and v equals ku cross v also equals v cross k v. So the position of the scalar k is very flexible, right? Okay, pay special attention here. U cross v is not equal to v cross u, but u cross v equals negative v cross u. So actually, these properties are not difficult to be proved using the Cartesian vectors. Here, let's consider the proof of one of the properties in the following example. And you can try to prove the others by yourself after this class, okay? Okay, next, let's consider this example. Proof for any vectors u, v, and w, and any scalar k belongs to the real number set. We have the following relationship. Okay, well, there is no scalar k, so just leave this out. Proof for any vectors u, v, and w, we have the following relationship. U cross the sum of v and w equals u cross v plus u cross w. So that's the distributive law for cross product. Okay, I'll give you 3 minutes to have a look at the question here. Then we'll have a look at the solution together, okay? Try to prove this by yourself. Well, I'll give you a hint. So you can try to use the Cartesian form of cross product to prove left side equals the right side. Okay, you can begin now. Okay, have we finished? Let's have a look at the solution together. We can let vector u equals u1, u2, 3. u3. The three components are u1, u2, u3. Three components for v are v1, v2, v3. And the three components of w are w1, w2, w3. Then let's find the left side. Left side is u crossed with the sum of v and w, right? So first of all, let's find the sum of v and w is v1 w plus w1, v2 plus w2, v3 plus w3, right? And the cross product between u and the sum of v and w is then given by the following expression. You can draw a diagram to help you to find the cross product. So the x component is u2 times v3 plus w3 minus u3 times v2 plus w2. The y component is u3 times v1 plus w1 minus u1 times v3 plus w3. The z component is u1 times v2 plus w2 minus u2 times v1 plus w1. Okay, so that's the left side, right? The right side equals, first of all, we find the cross product between u and v, and that is u2 v3 minus u3 v2, then u3 v1 minus u1 v3, then u1 v2 minus u2 v1. That's the three components, right? Then plus the cross product between u and w, which is given by u2 w3 minus u3 w2 plus u3 w1 minus u1 w3 j plus u1 w2 minus u2 wk. That's the three components for the second cross product. Then we can collect the like terms, right? So the component for component in the x direction is u2 times v3 plus w3 minus u3 times v2 plus w2. The component in the y direction is u3 times v1 plus w1 minus u1 times v3 plus w3. And the component in the z direction is u1 times v2 plus w2 minus u2 times v1 plus w1, which is exactly the same with the left side, right? Therefore, we have proved the original statement. Okay, do you have any questions? Okay, like I said, you can also try to prove the other properties by yourself using the Cartesian form of vectors, okay? All right, if you don't have any questions, let's consider another example here. Determine the area of the parallelogram defined by the vectors u4, 5, 2 and v3, 2, 7. Then determine the angle between vectors u and v. Okay, I'll give you 4 minutes to have a look at this question by yourself first, okay? Okay, I think you should finish now. Then let's have a look at the solution together. Okay, question A. We know that the magnitude of the cross product represents the area of the parallelogram formed by two vectors, right? We have already learned this in previous slides. So the area of the corresponding parallelogram is the magnitude of U cross V. So if you know the three components of U and three components of V, then you can easily find the cross product between U and V, right? So that basically the magnitude of 4, 5 to cross 3 to 7, right? Remember, you can always use a diagram to find the cross product between these two vectors. So that gives us the magnitude of vector 31, -22, and -7. And that's the square root of 1494, which is approximately 36.7. Okay, in question B, there are two methods. First, you can use sine theta, which is obtained from the cross product. Also, you can use cosine theta, which is obtained from the dot product, right? So first of all, let's have a look at if we use the cross product. The magnitude of U cross V is given by the magnitude of magnitude of U times the magnitude of V times sine theta, right? Since sine theta is given by the magnitude of the cross product time over the product of magnitude of V times magnitude of U. Okay, then put all the values in. That gives us theta is arcsine of this number here, and theta is approximately 47 degrees. Okay, so the angle between U and V is about 47 degrees. Since sine 100 degrees minus theta equals sine theta. Another possible solution is 180 degrees minus 47 degrees, or 133 degrees. A quick sketch will verify the angle is 47 degrees in this case. Also note that both of the corresponding position vectors lie in the first octant. So as you can imagine, if both of the position vectors lie in the first octant, then the angle between them should be less than 90 degrees. Sorry, should be less than 90 degrees, right? Okay, so like I said, there's a second method to find the theta between them, the angle theta between them. So this time we can use the dot product. Remember that the dot product between U and V is given by the magnitude of V times magnitude of U times cosine theta, right? Theta is the angle between the two vectors, and theta is between 0 and 180 degrees. Again, let's put all the values in. So cosine theta is given by the dot product between U and V over the product between the magnitude of U and V, which is approximately 0.6816. And theta is arc cosine 0.6816, which is also approximately 47 degrees, right? So also note that arc cosine is the angle between 0 and 180 degrees, right? So the angle you get here is exactly the angle between the two vectors. You don't have to sketch the two vectors in the Cartesian coordinates, right? You understand? So using cosine is more appropriate to find the angle between the two vectors, right? Because using sine, you have to decide whether the angle is an acute angle or the obtuse angle. You have to sketch the vectors to see which one is correct, because there are some ambiguous cases, right? But arc cosine gives you an angle between 0 and 180 degrees. So that angle is exactly the angle you are looking for. You don't have to sketch the graph. Okay, any questions? Okay, if not, let's consider another problem. Let's have a look at the applications of the cross product now. Okay, first of all, a little background. The torque, represented by Greek letter tau, is a measure of the force acting on an object that causes it to rotate. Torque is the cross product of the force and the torque arm, where the torque arm is a vector from the pivot point to the point where the force acts. In this way, the torque tau is defined as R cross F. R is a vector from the pivot point to the point where the force acts. F is the force act on the object point, right? And we also know by the definition of cross product, the magnitude of tau equals the magnitude of R times the magnitude of F times sine theta. And theta is the angle between R and F. In these equations, vector F is the force acting on the object. Vector R represents the arm, and theta is the angle between R and F. We use the right-hand rule to determine the direction of the torque vector. The unit of measure for torque is Newton meter, Nm. When we express the force in newtons and the displacement in meters, the units for the resulting torque are Newton meters. Okay, so according to the definition for torque, let's consider this example. Find the torque. A wrench is used to tighten a bolt. A force of 6 newtons is applied in the clockwise direction at 80 degrees to the handle, 20 centimeters from the center of the bolt. A, calculate the magnitude of the torque. B, in what direction does the torque vector point? Okay, I'll give you 4 minutes to have a look at the question here. Okay, let's have a look at the solution together. We can convert the displacement to meters. So 20 centimeters is 0.2 meters. Then translate the force F so that it is tail to tail with vector R. The angle between F and R is 80 degrees according to the given information. Then the magnitude of the torque, tow, equals the magnitude of R times the magnitude of F times sine theta. Put all the values in, that gives us 11.8. So the torque has a magnitude of about 11.8 Newton meters. Then by the right-hand rule, the torque vector points downwards into the material, right? Which means that the bolt is being tightened. Okay, do you have any questions? Any questions? No? Okay, then let's have a look at another concept, which is called the triple scalar product. Certain situations require combination of dot and cross products. The triple scalar product, A dot product with B cross C, is one such combination. Because the dot product is a scalar, this combination is only meaningful if the cross product is performed first. So, for example, consider the vector u, which is 4, 3, 1, v is 2, 5, 6, and w is 10, -3, -14. Can you evaluate the expression of u cross v? Then find the dot product of the u cross v with w. Then evaluate vector w dot product with u cross v. Then compare your result in part A and explain why this happens. Last, explains the geometric significance of the result. Okay, I'll give you 3 minutes to have a look at this example by yourself. Okay, let's have a look at the solution together. Okay, first, u cross v, then dot product with w. So first we find 4, 3, 1 crossed with 2, 5, 6, right? Remember, you can always use the diagram to help you find the cross product. So that gives us a new vector 13, -22, and +14. Then find the dot product between this vector and W, which is 10, -3, -14. That gives us 13 times 10 minus 22 times -3 plus 14 times -14, which is actually 0. Then in question B, you can also substitute all the values in and find actually the final result is also 0, right? So the answers in parts A and B are equal. This is because the dot product is commutative. So in the first question A, in question A, we first calculate the cross product between U and V, right? And then find the dot product between the new vector and W. Whereas in question B, also we find the cross product between U and V first, then find the dot product between W and this new vector. And because the dot product is commutative, therefore the two results should look the same, right? Okay, question C explains the geometric significance of the result. Vector U crossed with vector V is orthogonal to both U and V. Since vector U cross with vector V, then dot product with W equals 0. That means vector W must be orthogonal to U cross V and must lie in the same plane as U and V. Understand? Okay, then let's consider this example here. It can be shown that the volume V of a parallelepiped is given by the formula V equals A times H, as shown here in the figure on the right, where A is the area of the base and H is the height, right? Can you prove that the volume of the parallelepiped shown can be found using the triple scalar product W dot product with U cross V? Okay, I'll give you 2 minutes to have a look at this question, okay? Okay, let's have a look at the solution together. So recall that previously we have learned that the area of the parallelogram defined by vector u and v is given by the magnitude of u cross v, right? The height is given by the component of w that is perpendicular to the base. So let the angle between w and the height be alpha. Then we have the following relationship. H over the magnitude of w equals cosine alpha. Then H equals the magnitude of w times cosine alpha. Therefore, the volume of the parallel of height is given by A times H, which is the magnitude of U cross V times the magnitude of W times cosine alpha, right? Then we can change the order to find the magnitude of W first, then times the magnitude of the cross product between U and V, then times cosine alpha. By parallel lines, alpha is also the angle between W and the cross product U and V, right? Can you see that? Which is shown on the diagram on the top left, top right. So this is also perpendicular to the base. The cross product of U and V is also perpendicular to the base, right? Thus, by definition of the dot product, we know the volume is the dot product of vector W and the cross product between U and V, or by the following formula. Volume equals W dot product with U cross vector V. Any questions? Okay, so that's the end of today's class. Remember to complete today's homework and submit them onto Google Classroom before the deadline, okay?